My name is Charu. I'm the CEO and co-founder of Astra Optics Limited. We are a spin-off from the Chinese University of Hong Kong. We have a disruptive 3D printing technology in the nanoscale domain.
Could you help define what exactly is 3D nanoscale printing?
Semiconductor industry, for example, is in a micro-fabrication domain. So nanofabrication is even one scale smaller than that. So let's say, for example, a human hair is around 80 micron in diameter, and 1 nanometer is 80,000 times smaller. So nanofabrication involves making things which are much smaller than a human hair, or let's say around a human hair. At that scale of around, let's say, 50, 100 nanometers, anything below a micron, it's very difficult to manufacture things at low cost and in a 3D way. So 3D involves like a multi-layer fabrication. When you make something which cannot be done in a single layer, it has to be fabricated kind of like multiple times together, and everything has to align together to form a 3D structure. Like, let's say I want to make this, very small nanofabrication. So yeah, essentially it's like making something 3D, but smaller than a human hair.
And then what are the applications of 3D nanoscale printing?
So I would say there are two segments. One is the healthcare or research applications, which are mainly centered around healthcare, drug delivery, where there is a lot of research going on to go down to a cellular level so that we can solve the biggest health problems going down right into the nitty-gritties of the human body. The second major application of these technologies is in, let's say, electronics, consumer electronics, and I would say consumer electronics like smartphones, cell phones, AR, VR, LiDAR.
And then how prevalent is 3D nanoscale printing right now? And if it's not so much, what has been the technological barriers that have prevented it from proliferating thus far?
I would say there are two types of technologies. So one is the traditional old school manufacturing methods, typically used in the semiconductor industry. Those are traditional in the sense that companies have to commit a lot of capital investment in order to, and they have to commit to a particular design. So let's say they want to make some small electronics parts. Then you have to fix a design, make an expensive mold, which could cost hundreds of thousands of dollars and takes a long time to make. And then you're kind of committed to make millions of pieces to break even, right? So that's the traditional way things have been done. Additionally, in these traditional manufacturing methods, they are typically limited to 2D, like 2-dimensional or 2.5D manufacturing. If they want to make something 3D, they have to make one layer, then change the complete setup and add another layer on top of it. So it's a very complicated process. It's not at all easy, and it's very expensive. So each layer involves a lot of capital investment. So this is a well-known problem. People have been trying to introduce 3D printing as a way to like democratize. So the goal of 3D printing here is to offer companies complete total flexibility and to changing designs for printing or for making each part differently. It gives them the flexibility to do that. Also, it enables, it frees up all the capital investment. So if you want to make one single part, you just have to upload a design of that, and then the printer would just print it. So it's like, when you take an Uber, you only pay for the ride. You don't have to buy the whole taxi ride. So that's kind of the true value proposition of 3D printing. So currently there are technologies in nanoscale 3D printing or nanoscale 3D printing technologies. However, they are not yet that cheap or not yet that inexpensive that this can be achieved. So they're still quite slow and expensive. So while they can make 3D structures in one go instead of instead of like having completely different processes for each layer, they can just build parts in a 3D way. However, they're still a bit more expensive. They haven't really unlocked the true potential of 3D printing yet at that scale.
What are the advantages of 3D versus 2D printing?
I guess it allows us to make much more complex structures much more easily, and they are homogeneous. So the structure is like a monolith, right? It's built in one go. So its physical characteristics may be much better. it's just way simpler. It's way simpler to make things. If you're printing some 3D structure in a traditional way, every layer involves a complete new design. In electronics, right, in the semiconductor industry, it involves every step, every layer involves having a photo mask, right? So you have to fabricate a mask to transfer certain pattern that you want to transfer to that layer. Then once that layer is built, then you move on to the next layer where you sometimes have to also uh, deposit sacrificial material and then your target material, and then clear out the or etch away the sacrificial material and then move on to the next layer. Again, there could be many restrictions on the design because each layer has to, it can only build up one layer on top of each other. 3D printing just allows you to have much more flexibility in terms of the design. For prototyping, again, 3D printing is really great. It allows people in the early stages of design to just experiment very quickly. In research applications, 3D printing is probably the only way to achieve what they want to do, because those are low volume applications where the semiconductor processes, I guess, they don't make much sense because they're in the experiment stage. The volumes are always going to be low, so it just the investments just doesn't make sense.
What sort of innovation is Astra Optics, your company, bringing to the space of 3D nanoscale, and how is it solving some of the problems that you might have mentioned before?
So like I mentioned earlier, the current state-of-the-art nanoscale 3D printing technologies, they are still quite slow and expensive. So they haven't really truly unlocked the potential of 3D printing at this in this domain. And they suffer from, let's say, four critical bottlenecks, all of which we are the first ones to solve them. So we are the first ones to really enable scalable 3D printing in the nanoscale domain. So those are, number one is speed. So we are, let's say, 100 times faster than the state of the art 3D printing. And compared to traditional nanoscale like fabrication, 2D fabrication, or we are probably millions of times faster because those technologies are just way too slow. So, so number one is speed. The second is cost. So because our speed is so high, the cost of making a part or the time to make a part is, let's say, only 10%. So actually the cost to make a part is only 10% with our system. So because in this 3D printing technologies, the cost is basically the amount of time a laser is operating, right? So, and these lasers have limited lifetimes, let's say around 20,000 hours. So every hour you use is basically money, right? It's cost. So because we're so fast, we can drastically bring down the cost to make a part. The third bottleneck is material variety. So most of the nanoscale 3D printing technologies can only print polymers or, let's say, ceramics. So they're only limited to those two or very limited set of materials. Whereas our technology, we have demonstrated and print over 20 materials, including semiconductors and, let's say, biocompatible materials and lots of other metals and oxides and other materials as well. But that's actually we are one of the first technologies that can do that repeatably. And the fourth bottleneck is precision. So like I mentioned, which I didn't mention, but most of the 3D nanoscale technologies, 3D printing nanoscale technologies are based on lasers. So we use a powerful laser to basically solidify a polymer and make a 3D structure, right? But because we're all based on light, there is a limit based on physics, let's say a diffraction limit, right? So it's difficult to make something smaller than, or some features on a part smaller than 100 nanometers typically for this 3D printing. However, with our technology, we have been able to go down to 20 nanometers. So for the first time, we are enabling people to make things smaller than 100 nanometers with different materials. So that's another huge bottleneck we are solving. It's again, the use of this would be more for scientific applications, scientific breakthroughs. So yeah, so we are solving these four important bottlenecks that unlock lots of doors, both for industrial applications to like democratize 3D printing, and as well as it can enable scientific breakthroughs in lots of domains.
Can you talk a little bit about the business model that Astra Optics is employing to deliver the value promised by your technology?
So we have two. different business models for two segments of the market. For industrial applications, we would probably focus more on 3D printing as a service. So let's say a fab wants to, custom design some new diffractive optical element, let's say like a lens, a very small lens. So then they can just order, so like 3D printing on demand. So they can place an order to us with us, send us some designs, specifications, and then we just print out the structures and then ship it to them. So I think for industry, that model makes a lot of sense. The other model, which we will more focus on our other target market, which is scientific applications, so universities, research labs, that would be to sell our product, sell our platform, so sell the whole 3D printing system to the universities or scientists. So the reason is scientists prefer to play with a powerful platform like ours, typically in this space, and they they like to just keep. Uh, so let's say typically 3 or 4 or 5 groups will collaborate and buy this system, and then use it for let's say 10 different applications, and print with different materials, play around with the system, configure it the way they want to. So it's more like a developer open access system. So yeah, those would be primarily our two business models.
How difficult would it be for kind of a large existing manufacturer, whether it's a fab, to undertake your technology if you were to, for example, license out the platform to them?
So for industrial applications, we for prototyping we fit really well into the existing manufacturing supply chain or manufacturing process. So typically, when a company wants to make a new component, let's say a new optical part or a photonics device, then they have to design it, then prototype, and then test it, and then once once everything is good, then they can commit their capital investment to manufacture, right? So even if we just replace prototyping, so prototyping also we can offer a lot of value, because currently prototyping is done typically with the most expensive methods such as electron beam lithography or even photolithography, and the cost of that is usually hundreds of thousands of dollars, and the lead time can also be months, 2, 3, 6 months, even 12 months. So we've been talking to companies, and they're struggling with these two problems. So they're actually ready. They're already sending us designs, and they want us to print to replace their prototyping, just their prototype. And we can also move into actual production. So that would just completely replace their existing processes. They would just not need most of the processes if we can go into actual part production, which requires matching all their material properties. So we might have to develop some material recipes to fulfill the functional needs, right, of some devices. Yeah, so it's possible to replace their entire supply chain, but only for certain types of parts. I think it's more practical. Yeah. Otherwise, it would be more kind of how do we fit into or how do we integrate ourselves into their entire manufacturing process.
What does the future of manufacturing look like given the type of technology that you're deploying right now and perhaps other technologies that are out there?
In healthcare, the technologies like this could completely change to completely revolutionize healthcare. For example, imagine if we could have like an army or a swarm of nanorobots, let's say like drones, right? But they're so small, they can go into your body, into your blood vessels to carry out different functions, to, let's say, deliver drugs in a particular location, or even perform some complicated surgeries in the brain or the heart, remove a blood clot, but non-invasively, right? So you can just really like inject an army of nanorobots right into your bloodstream with like an injection. And our technology, for the first time, enables making such small things that can actually realize these functions. So lots of research groups all around the world are working on problems like this. There are already lots of groups working on micro robots, and they're still in the early stages of research, where again, typically they run into some of the bottlenecks that I was talking about, that these 3D printing technologies that currently exist are limited by the resolution, how small they can make a feature, and then the materials are limited. So there are papers out there that talk about this. Another example, metamaterial is an engineered material that can overcome these limits by stacking the smallest units in a different way, or changing their structure, just like we do it in a large scale in buildings and other larger structures. We can, or bridges, right? So we can do the same at a nanoscale, and that can make these materials much stronger than what they're naturally in their natural state. Another one is materials. Why is it so valuable, right? So let me give you a more concrete example. So you can make a material, you can reduce the mass by making it hollow and or specific truss-like structure. So that increases the strength to weight ratio of structures. So for applications in space, for example, that's invaluable, right? Everything has to be, the lighter the better.
If people want to find out more about Astra Optics and the technology and the breakthroughs that you're achieving, where can they find out more information?
So you can go on our website. It's www.astra-optics.com. That's ASERA-optics.com. You can also go to our LinkedIn page, Astra Optics Limited. You can find us on LinkedIn and reach out to us by email, LinkedIn. Our email is info@astra-optics.com.